Hello, I'm Simon Barner from Fortis Research Institute in Munich. In the last part of the tutorial, I gave a general introduction to the Autofocus 3 toolset and demonstrated to you how the logical architecture of such system can be modeled. In this part of the tutorial, I will focus on the description of the platform architecture using Autofocus 3's technical view. The corresponding model covers both the underlying hardware platform as well as the virtualization layer. The platform architecture model is hierarchic and defines the involved platform elements such as the execution units, the transmission units, memories and gateways between different levels. It also describes the interfaces of these platform elements. In addition to that, it is possible to annotate different extra functional properties to the platform elements such as the clock speed, of course, power consumption, and so on. While Autofocus 3 supports a number of generic and also in general different platform architectures, in this tutorial I would like to focus on a platform model that can be used to describe platforms based on the DREAM's architectural style summarized in the first part of this tutorial. At first, a platform architecture is created. DREAM systems are grouped into logical clusters. A cluster consists of a set of nodes, that is, embedded computer systems that communicate over an off-chip network. As shown before, the off-chip networks of different clusters can be connected using a gateway. A node consists of a number of multi-core chips that communicate over an on-chip network. The connection of the on-chip network to the containing nodes off-chip network is realized via a gateway. The platform architecture model provided by Autofocus also allows to model the internals of a tile, that is, the involved processing cores, the involved buses, as well as the memories that are installed in the system. Furthermore, also the interface to the containing tiles on chip network can be described. For each tile, the virtualization layer can be described, that is, the configuration of a hypervisor. Here, the different involved resource partitions, their configuration such as the accessed memory areas, as well as the communication topology within the hypervisor, that is, the interpartition communication, can be described. Furthermore, it is possible to specify how the hypervisor accesses the on-chip network of the underlying computation tile. The deployment model provides a means to connect the logical architecture and the technical architecture. For this, it provides model elements to define mapping between components of the logical architecture to execution units, as well as ports to transceivers. Deployments can either be created manually using a graphical editor or automatically using a design space exploration that will be covered in the last part of this tutorial. In addition to the mapping information, the deployment model also provides means to define deployment-specific parameters that depend on the mapping of the different components to the platform, such as the estimated WCT or the consumed energy. These are used then for the automated design space exploration algorithm. In addition to what has been presented before, Autofocus also supports models at different layers of abstraction that are used in other phases of the development process. On the one hand, this comprises requirements models that can be used to define the system context, both in a formal or informal way based on patterns or a glossary, and it allows to trace these requirements to the corresponding implementation architecture. Another emerging feature in autofocus are safety cases. These are a proven technique to perform systematic argumentation of the system safeties. They provide techniques to decompose complex arguments based on the modular system artifacts created during the development of a system. In autofocus 3, the goal structuring notation is used that is a well-known approach to formalize safety cases.